Hello everyone and welcome back to another class of fundamentals of particle and fluid solid processing. So, we were discussing about the fundamentals of particle size reduction and associated laws that dealt with the energy requirement for this size reduction. So, we have seen three laws in chronological order. One was the Rittinger's law, Kick's law and Bond's law. So, these three are again summarized in the slide. So, this first one is the Rittinger's law. First is the integral form, the second one is the differential form. Similarly, in the second row we have Kick's law, integral form and the differential form, and the third one is Bond's law, which has integral expression of this kind and has a differential expression of this kind. So, now by looking at these differential expressions, several researchers have proposed that all these three can be considered as the integrals of same differential equation or similar differential equation when this index of n changes to 3 values. So, these three in generic expression can be written in this form, which is d by dx is equals to minus c divided by x to the power n. Now, this exponent n, when it is 2, c becomes Cr, which is the Rittinger's law constant, and the expression represents the Rittinger's law. When it is 1 and c is Ck, which is the Kick's law constant, it represents the Kick's law, and when it is 1.5, it is the Bond's law. So, basically this summary helps us to understand the energy requirement for a particular operation as well. So, what happens if we look at the forms of these three expressions? The reason being we are able to write this in a generic differential equation is that when first Rittinger's law came up, it is modified by Kick and then further it has been modified by Bond. So, it was the improvement of certain hypothesis, and with that we can say that the energy requirement or the prediction of energy requirement for a certain design improves with these relations or expressions. Now, we have seen that Rittinger's law was not valid for certain reason. Kick's law was also obsolete for the size ratio variation, and then the Bond's law came up. Now, it has been seen that all these three can be reliable if it is used within the certain range of size range. That means, basically these expressions were derived for a certain range of size particles. These are the empirical relations. Several experiments were done for different systems for different size ranges. It is not an exhaustive size range that has been studied. So, if we look at the specific energy requirement predictions by these three laws, we see that these three laws works pretty well within their proposed or within their derived size range or the range, the particle size range. So, in this diagram, it is in the y axis we have a specific energy requirement, and in x axis we have the particle size. So, and this is in log scale. because of the expressions that we have seen. It is pretty logical to put this in log scale, and we can understand the slopes of these curves from those expressions. Now, here we can see one interesting point, that these dashed portions are the extrapolated ones. All the dashed portions are basically the extrapolated one. So, this is for the Bond's law, this extrapolation was on Rittinger's, and this one was for Kick's. So, typically, and during the discussion of the derivation also, I mentioned that Rittinger's law provides us reliable prediction when we deal with the ultrafine particles, and we can see that this hard line basically comes to near about this value, which is in the order of microns. Bonds works from about micron range to 100 micron range, very satisfactory. And for the coarse particles, we have Kick's law. Now, if we look at those derivations once again, we can realize that the Kick's law dealt with the size ratio, final and the feed particle size ratio. Rittinger's dealt with the surface area, and Bond's law worked in the intermediate region, and that is what is reflected in this diagram as well, that when there is huge amount of surface creation, and that is for the ultrafine particles to finer particles, Rittinger's law provides us a reliable predictions. When we deal with the coarser particles or coarse crushing, Kick's law can safely be used as initial estimation. And Bond's law or the Bond's formula suitable for intermediate particle size, which I mentioned earlier, that this intermediate size is actually extensively used in industry applications, and that is why Bond's law is more popular than the other two. Another interesting feature that is apparent from this diagram is that the Kick's law says that the specific energy requirement is basically dependent on the size reduction ratio, which is reflected here. It is a fixed value. It is not dependent on the particle size. It is the particle size, the reduction ratio, the initial particle size divided by the final particle size. So, this is the summary of the energy requirements for this size reductions. Now, we move on to one problem to see that how these expressions are used, or which one would be more reliable predictions. So, for here the question is, a material is crushed in a crusher such that the average size of particle is reduced from 50 millimeter to 10 millimeter with the consumption of energy of 13 kilowatt per kg per second. That means 13 kilojoule per second per kg. 13 kilojoule per kg. So, what would be the consumption of energy that would be needed to crush the same material of average size 75 millimeter to an average size of 25 millimeter? Assuming the Rittinger's law applies, and assuming the Kick's law applies. So, we will see that the same problem, if we apply two different laws, how or what is the difference in the magnitude that these predictions will provide us. So, the problem is very much straightforward. We have x1 as 50 millimeter to x2 of 10 millimeter, and for this the energy requirement E is 13 kilojoule per kg. If that is so, what is the energy requirement when this size reduction would be from 75 millimeter to 25 millimeter? We have to apply both the laws, that is Rittinger's law and Kick's law. And the last part is that which should be regarded as being more reliable and why. We have to provide explanation for that. That we will get one E1 from here and E2 from part B, and which one is more reliable for the design. So, very straightforward simple problem. By Rittinger's law, we can write this expression that the energy consumed is equals to Rittinger's constant multiplied by 1 minus x2, 1 divided by x2 minus 1 by x1. These values initially are given. We have to basically calculate this Rittinger's law constant, which we can find numerically. Using this, because this is the same equipment is being used for crushing material from 75 millimeter to 25 millimeter. So, the Rittinger's constant would be same because the material and the machine is same. So, using that constant, we can now calculate the energy requirement from 75 to 25. That provides us the value 4.33 kilojoule per kg of energy required. Similarly, we apply Kick's law. We initially find what is Kick's constant by replacing all the numerical values of known quantities. Using this Kick's law constant, and for x1 is equals to 75 and x2 is equals to 25, we can find the energy requirement, which is 8.88 kilojoule per kg. So, from Kick's law, it says we have an energy requirement of this much, 8.88. From Rittinger's, we had 4.33, double of that. Huge difference in predictions. So, now comes the third part, that which one is more reliable and why. One of the logical point, that since this is the initial estimation that we are having, whichever is higher we go with that, because that is safe or safer. But the point is that it is logical, but at the same time it is inefficient if we do not judge that why it is so. If we utilize say most of the energy and taking that into consideration for the design, we may be overestimating everything. So, here which one is more reliable? For that we have to look at the size reductions. Now, the last slide to this problem we mentioned its validity, that is the Kick's law for large particle size or coarser crushing and Rittinger's law for the ultra fine grinding. Now, here the size range, is it the ultra fine or the finer, or is it a coarser? So, from 75 to 25 millimeter it is not considered as fine particles or range of fine particles or generation of fine particles. It is a coarser grinding. That means the Kick's law prediction is much more reliable, because it closely relates with the energy required to effect the elastic deformation before the fracture occurs, which leads to more finer particle. So, I hope the reason for selecting Kick's law prediction is clear for this problem, and in general how do you decide when such problem occurs. You can calculate this energy requirement by all the three methods, kicks, retingers and bonds, and if you have to choose, then look at the size reduction ratio. Is it for the coarser particle? Is it for the finer particles? What the ultimate result that you are producing? What is the desired product size that is happening, and from where it is happening? If you see there are chances of huge surface area creation, then the energy required would be more reliable from the retinger's prediction. If it is the coarser, go with the Kick's law. If it is the intermediate, go with the Bond's law. So, I hope this selection is now clear to you. And this brings to the introduction of some equipments now. A brief overview of the equipments that are typically used in classical size reduction process. Now, the choice of this comminution equipment depends on the stressing mechanism. This we elaborately have discussed. We have also mentioned that what is the size reduction ratio that you are looking at it, that what is the feed size and the product size. Based on that, we have to choose the appropriate or suitable equipment. So, basically choice of equipment depends on several criteria. The dominant or one of the most important is the stressing mechanism, the kind of particle that you are trying to achieve, because such kind of particles will come from different stressing mechanism, or the combination of stressing mechanism that would lead to several ranges of products. So, we will see that when we have an overview of these equipments, that how those equipments are using which of the stressing mechanism. The other logically important parameter is the material property. Based on its physical properties, its strength, appropriate equipment has to be chosen. If it is not just the solids, if it is being carried with a certain carrier medium, then that also dictates the choice of equipments. If the materials are abrasive and being carried in terms of suspension, it cannot be used in all the classical machines that we have for size reduction. The other parameters are the mode of operation, its capacity or the throughput that you are looking at, the rate at which the product should be out from that equipment, and its adaptability with the other unit operations, because it is not just an industry is working on the size reduction. It is one of the part that comes at the upstream for the desired product. So, it is fitted or associated with several other unit operations. So, its adaptability to the other unit operations, that also dictates this choice of equipment. Now, this stressing mechanism, we again and again stressing on this particular point, because broadly the equipments works on this one of such or combination of such stresses that can be applied in a manner that can be applied. So, these can be broadly categorized in 3 ways that is listed here. One is the crushing plus attrition. We outlined this thing, we have seen this thing in the last class as well, that what is the difference in the crushing, impact and the attrition. So, typically this combination of these two are there in certain equipments that works on the principle that there are two surfaces like surface particle or particle particle. These influences or effects in this crushing plus attrition mechanism, and when there is low velocity operation in the range of 0.01 to 10 meter per second. So, it happens like this crushing plus attrition, that you have two solid surfaces and it is crushed from both the sides. So, in this case, if this is a lump or a block of solid, it is just the crushing. There are stacks of solid particles. Here crushing plus attrition, that is in between particles, also comes into play. Instead of this solid surfaces that crush from both the sides, it can be some fluidic media with a high impact that can also crush these particles. The other can be the impact plus attrition. Attrition is typically there. In some cases, it is less dominant mechanism. Typically, the dominant mechanism predominants are the crushing impact, okay, and the shearing actions. So, in impact plus attrition, what happens? A single solid surface is involved in that operation. So, either the solid particle hits the surface or that surface hits the solid particle, be it a solid or the fluidic media, or fluid when there is a high velocity of the fluid and the particles are being carried. There the particle particle attraction or the attrition will cause this size reduction to happen. The third mechanism can be the stress imparted by the carrier medium, that is the wet grinding, deagglomeration, such kind of phenomena. So, based on these mechanisms, the existing equipments can be classified, or in other way, this equipments works on one of these mechanisms or combination of these mechanisms. So, for example, if we look at the jaw crusher, what happens here is that we have a static jaw. There are two solid surfaces in which one is fixed, the other one is hinged at the top upside, and this has a jaw action which crushes the particles when the particles are fed from top and discharged through the bottom. So, it is a moving jaw and this is a static jaw. So, it presses against the static jaw and the solid particles are crushed. Now, since you can understand here can be multiple particles, if there are different size range, the mechanism that is involved is the crushing plus attrition, attrition between the solids and the surface, and the crushing between two solid surfaces. Now, in this case, the interesting phenomena is that depending on this discharge size, the particle size range or the outlet particle size range varies. So, you can control the product size range by adjusting this gap at the outlet or the movement of this impact. If it is smaller enough, it will be discharged through the wires. The second one, say the gyratory crusher. Now here what happens is that we have a section, a closed chamber, where the surfaces are the crushing jaws, static one, a static chamber, and this kind of shape of a head is there which rotates inside the static chamber. This is the axis of rotation. So this acts as a gyratory head which rotates, and the particles that comes and flows through this annulus or this gap between the gyratory head and the static chamber, where the static chamber surfaces are, the jaws are there, it crushes the particles whichever comes in between these two surfaces. So similar to the jaw crusher, in gyratory crusher also the mechanism involved is the crushing between the two surfaces as well as the attrition between the particles plus the particles with the surface. Now in this case, the product size can be maintained by adjusting this gap, which can be adjusted by placing of this gyratory head in appropriate manner. So this whole thing can basically be adjusted or placed to adjust this gap. So the particles of sizes lesser than this gap will come out from this chamber. Until and unless that happens, it stays in the chamber and the crushing goes on. So one thing is very clear, that this size reduction process of handling solids is very prone to wear and tears. The other mechanism with just the crushing, we can say, is the crushing roll or the roll crusher, which is very popular. So here what happens, there are two rolls that moves in the opposite direction. Feed comes in from the top, and due to this opposite motion of both the rolls side by side, it takes the solid, it attracts them towards this gap where it is crushed between the two surfaces. And in this case, these positions are adjustable, which means this gap can be adjusted by placing these two rolls in a suitable distance or appropriate or the desired distance. So in this case, typically crushing is the dominant mechanism, stress mechanism. We will continue this discussion on different types of equipments in the next class. Here we have seen the summary of the energy requirement that was predicted by different laws, its applicability, which one is more reliable, the different types of equipment mainly based on the crushing plus attrition mechanism. There are other mechanisms which we will be discussing in the next class.